we studied the unitarity of the S operator and decided to push its boundaries, literally, because we took a term that is not usually considered in books, okay? So which was the term corresponding to a one-particle exchange, okay? And from there, just by itself, we concluded that the following must be true, okay? So if you did it, hopefully you did it carefully, following the start and everything, and then translating. If you translate that into the language of matrix elements M, this is what you should have gotten, okay? We also said that it would be nice to introduce a diagrammatic notation for this, because it takes too long to write this all the time. So we said that we wanted to denote this as a blob which has two arrows, PA and PB incoming, and N arrows, P1 through Pn outgoing. So this in the limit when PA, PB plus PB squared go on shell, meaning that the value goes to M squared, should look like PAPB going into Q. So we have this strange object here, but which is just a pole. Now there is something remarkable. Not only is a pole, it's a simple pole, okay? So unitarity tells us that this object as a rational function can only have simple poles, okay? And so we have another blob here, P1 up to Pn, going into Q star. Now this picture is almost beautiful. I mean, it almost wants to tell you something interesting. It's almost there because you could imagine intuitively that if you scatter particles and you tune their momenta so that they can produce another particle that is physical, you should expect that this object will scatter, will produce that particle, and that particle can perhaps propagate for a long time and then decay into the other particles that you want to see in the final state, produce the other ones. So this is almost telling us that story. These two particles coming in, producing this one, but this is kind of a mess. It's almost what we want, but not quite, okay? This actually looks strange. This is the conjugate of particles P1 through Pn coming in and producing particle Q, okay? It would be ideal if we could fix that little problem. Any ideas on how to fix it? Sorry?
Okay.
Yeah, so we learned something else yesterday, which was crossing. So what was crossing? Well, we said that in our fancy new notation, well, maybe we should use the old one first. So we said that if we have this matrix element, say of particles of any number of particles coming in, say with some particle Pi here, going into any set of particles here, okay, that this matrix element as a rational function of momenta, okay, that's an important thing we should keep in mind, as a function. So if you compute this function, and we will, okay, perhaps not today, but we will compute this function, is the same as a function that you will get if you compute it. So maybe I should use the notation. Well, this notation means that we have removed Pi from here. It's not here anymore. And we put it as a final state with momentum minus Pi. Okay? Well, to be more precise, if there are other quantum numbers, as we now know, right, because we have this sigma that we were discussing for the one particle states, so if this particle also had other quantum numbers, like the sigma we had yesterday. Yesterday, we were classifying one particle states by P and sigma. Then these quantum numbers could also change when you go here. So I'm going to allow the new quantum number here to be sigma bar. In our quantum field theory course, we will see that what happens is that a particle goes to its antiparticle. Okay? But for the time being, let's just say that we have some quantum number sigma, and it goes to sigma bar. So if we have this, we can immediately apply the suggestion that we had, which is, well, why don't you try to fix this using crossing? Well, let's fix it. So if we use crossing, that little term over there that is annoying can be replaced by a picture where we have minus q incoming and minus p1 through minus pn outgoing. Okay? Of course, if we keep track of the sigmas, of the internal, of the other indices, sorry, then this one will have indices bar. While the indices that we had here were sigmas. Okay? Because we're using crossing. Now, it turns out that computing the star, the conjugate of this object, as we will see in the quantum field theory course, is an operation that is called parity. Actually, parity in the full sense of the four-dimensional space. So we are flipping momentum and sending it to minus momentum. Okay? But it also flips these quantum numbers. So when we do parity, we get Q going to P1, Pn, and with the quantum numbers sigma, the original ones. So isn't that nice? We fix our equation. It's just as beautiful as it gets. So unitarity is now the statement and I'm going to fix it here. That this must happen. Okay? Well, some of you might have seen this before. This quantity, even with the I epsilon, is what is called a Feynman propagator. So this is somehow telling us the tale of a story, something happening, propagating, and then producing this. Okay?
One question. We derived this result of the M working just with the resolution of the identity with the first particle and using the eigenstates of momentum, right?
That's right.
So the first question is, those eigenstates are the same eigenstates of the generator of translations?
Yes, of the momentum operator, yes.
So what we did in the first class is implicitly, I mean, what you write as the ket or the brow P implicitly has the other quantum numbers inside, right? Which
Yes,
is the sigma.
yes. In all the lecture yesterday, we could also have kept the sigmas from the beginning. Yes, very good. Okay. Precisely, that's what we're going to discuss now. And we can use this board because it's dry. So we ended the lecture yesterday by discussing one particle states. And we said that they were defined as eigenvectors of the momentum operator. And we decided to classify them by the way they transform under Lorentz. Okay. So we ended the lecture having derived the following. If we take u of lambda acting on p sigma, okay, this has to be a linear combination of all possible particles with momentum lambda p, and with all possible extra quantum numbers, sigma prime. So it must be a linear combination. We just sum over all sigma primes with coefficients that depend on sigma prime, of course. Sigma, because it's the original state, and the transformation we are carrying out. And it's also good to introduce a momentum. So it basically depends on everything on this side. Okay. And the job was to, or what we said we were going to do today, is to classify the possible transformations. Okay. What are these C's? Or what are the possible values of the extra quantum numbers sigma? So in order to do that, so the mathematical statement of what we want to do is to classify all possible representations. Okay? More precisely, all possible irreducible representations. And there is a trick for that, and it's the following. The idea is to introduce a reference vector which Weinberg calls K, and we're going to stick to the same notation, and say that once we fix that reference vector, we can construct any other vector in particular P as a Lorentz transformation on K. Okay? Now, it's convenient to give a special name to this Lorentz transformation, and then we're going to call it LP. So it's a Lorentz transformation that takes K into P. But is that unique? What do you think? Nope. Very good. It's not unique. There are tons of transformations that can take K to P. In fact, if we first apply any transformation that doesn't do anything to our vector K, in particular any rotation transfers to it will do nothing to K, and then apply your favorite transformation that took K to P, then we will just be constructing new transformations that do the job. Okay? But in any case, I'll just choose one. And I'm going to call it LP. Very good. So once we do that, we can define what we mean by this state. So this is a definition. We're going to define what we mean exactly by this state as my particular choice of transformation acting on my reference state. Okay? So I'm just choosing representatives in this space, or I'm choosing a particular way of mapping these states into these states. Okay? Very good. Now what do I want? I want to see how a Lorentz transformation acts on these states. Hopefully, I'm going to be able to learn how this works, in particular this, by solving a simpler problem. That's the idea of doing all this. Okay? So we want to apply this to this state. So we have u of lambda, u of L of P, K sigma. This thing here combines into this Lorentz transformation. Okay? But I want to translate this back into something that has this structure. Okay? But according to my definition, the way I'm going to get this or the way I've defined these states, is by applying some particular Lorentz transformation on my reference states. Okay? That's how I'm defining this. So I want to get something like this from that state. Well, if I want to get something like this, I better apply this transformation here. But I cannot just put it there. So I have to put the inverse as well. Yeah, okay? So I'm just inserting the identity, but I'm telling you why I'm doing it, because I want to have this acting on something that will bring back these states. Okay? Any questions about this step?
Sorry, could you go over the reasoning behind that again, please?
Yes. We want to get a formula like this. Remember, that's our aim, to get to something like this. Well, in this formula, these states enter. But these states are defined, remember, I'm choosing the definition, to be these Lorentz transformations applied to this. Okay? So that's the motivation for introducing this, because I want to have this somewhere in my equation, because I want this operator to act on something. Okay? Well, in any case, I mean, that's just the motivation. I haven't done anything that you could also think this is just a trick. I mean, I just decided to introduce the identity in this form. I'm just trying to motivate why. Okay? But if you don't like my motivation, let's see where we get, and then you say, oh, the result is a good motivation for doing that. Okay, so having done this, now I'm going to put this inverse inside. I shouldn't do that. So I'm going to put all this together as U. The inverse goes inside. It composes with this. I have L inverse, lambda P, lambda LP, acting on K sigma. Okay? Very good. Now, what is this Lorentz transformation? Well, this is a Lorentz transformation that takes the vector K, right? It produces a vector P, okay? Then it produces a vector lambda P, but this guy precisely takes me back to K. So this strange object here it's a Lorentz transformation I'm going to call W, and it's precisely this redundancy or this choice that I had in defining my vector K. In other words, it's the set of all possible Lorentz transformations that do nothing to K. Okay? Now, do they form a group? What do you think? If I have two Lorentz transformations that do nothing to K, when I compose them, do I get another one that does nothing to K? Yes. And the identity belongs to it, of course, because the identity does nothing to K. So the set of all possible Lorentz transformations so W belongs to the set of all possible Lorentz transformations that leave K invariant. And this happens to be a group by itself. But of course, it's a subgroup of the Lorentz group. So this group is a subgroup of Lorentz. And it has a name. It's called the little group of K. In more fancy terminology, in fancier mathematical terminology, it's called the stabilizer of K. It's a subgroup of things that do nothing to k. Okay? Now, why is this great? You may wonder. Well, the reason is that we're now saying that if we apply UW to k, this transformation should keep us in the sector of our Hilbert space of all with momentum k. Okay? It shouldn't move us away from the sector that has momentum k. But we haven't said anything about sigma. It could actually move us in the space of sigmas. Okay? So this transformation can actually change sigma, but it cannot change k. So in general, this transformation will keep us in the space, but it must be that this is a linear combination of all possible states of this form with momentum k. And now this depends on, well, everything, right? So you might say, well, we haven't done anything. I mean, we started with that equation, and we ended up with this equation. And now the problem is to classify these things. Can anyone see the crucial difference between this problem and the problem we had over there? What's the crucial difference?
We have the same momentum.
Sorry?
We have the same momentum.
Exactly. We have the same momentum, so we don't have to worry about that. So we only have to worry about possible representations of a group without worrying about what happens to the momentum. What else have we gained? That we're studying representations of what? Yes, but I mean representations, say, into matrices, but representations of which group? Of the little group. So the little group is a subgroup. So studying representations of a smaller group is easier than representations of a larger group. So this thing bought us two things. Yes?
How is W generated? Like operationally from the
Well, apply all possible lambdas.
So I pick an L and then I apply all possible
Just apply lambdas.
from the bigger group.
No, lambdas, Lorentz transformations, right?
Yeah.
And then that thing is always in the little group.
Question.
Yes.
I'm having trouble. So I'm trying to figure out what L is some particular Lorentz transformation that'll always, given P, will take me.
Yes,
down.
so we make a choice, yes.
So why could so if I was to pull that in that expression for W, if I was to pull that lambda inside the L, I'll just get the identity and that'd be useless. So you're saying L and lambda, there exists more than one transformation?
Well, we started the discussion exactly. And precisely how many transformations are there are classified or are parameterized by the elements of the little group. That's how we started the whole thing. Very good. That's excellent. Okay, so we're done. Well, we can go home now. Not really. We got here, right? We got up to here, so let's actually use it for something. Let's study different cases, okay? So we have to choose some reference K, okay? Well, but which reference case we choose actually depends on the mass of the particles we're considering. The reason is the following. Imagine that we have, say, particles of some mass, m. I'm going to say greater than 0, because later on we're going to consider the case with m equals 0, okay? So massive particles. In the case of massive particles, we know that we should choose a k that does this. Well, what would be your choice? I mean, if I give you, pick any k that does this, what would be one of the simplest choices? That's right. M0, 0, 0. That would be the simplest choice, right? Now, what is the subgroup of the Lorentz group that preserves this? Rotations, standard rotations in the space, x, y, z, right? So the little group is SO3 or rotations in space. Okay. Now, do you know the classification of irreducible representations of SO3? What is a classification? How are they classified? They are classified by numbers, right? Yes. So here there is something interesting, right? So usually when you classify the representations of groups, you start by classifying representations of its algebra. So you start by classifying the representations of the algebra of SO3, which is isomorphic to the algebra of SU2. Okay? And these representations are classified by a quantity J, which can take half-integer values. Okay? Now, this number, people like to call it S, and it's precisely what is called the spin of the particles. Now, SU2 as a group is not the same as SO3. Shocking? No? Right, you all know that, right? So SU2 as a group is not the same as SO3 as a group, right? But acting on the Hilbert space, we are allowed to have these minus signs floating around. So actually, quantum mechanics tells us that even the half-integer representations are allowed in nature. In fact, it's fascinating that we see them, right? Very good. So this is what we mean by spin. Now we have the two numbers that people usually talk about. The mass of a particle is a Lorentz invariant, and the spin of the particle is another object, is another number that we can use to classify things. Okay? Well, in fact, we could now use this formula there. Okay? Yeah, in fact, I should have used before jumping into this. But, I got a little bit ahead of myself. So really, the final equation we wanted to write was the following. So we're after this U lambda of P sigma, right? And remember, we did all that just to have this guy here. That was the whole purpose of the exercise. And then on the other side, we have this, so we can plug that in here. Now, these are just numbers, or matrices, if you wish, in terms of sigma and sigma prime. So we can pass this operator through. These are just numbers, because these are the coefficients of the linear combinations. So when we pass this and hit this, what do we get? Well, this is what I wanted to get.
So summary is sigma prime.
Thank you. So once I have the classification of representations of the little group, I can straightforwardly use them to solve my problem. Okay? So for every irreducible representation of the little group, I can induce a representation or construct a representations of the Lorentz group. Okay? And this is really the equation we wanted to get, connected to the formula that we have over there. So for every one of your favorite representations here, you can just use them into this equation and construct a representation of the full Lorentz group. Okay? Now, those are massive particles. Do we know any massive particle in nature, a fundamental particle? Has anybody ever seen an elementary massive particle?
that the electron has mass, but I'm assuming you're referring to the Higgs thing.
Yeah, that's right. So before last year, we hadn't. So now we know there is one, and we believe it has a spin 0. So out of that whole list, as an elementary particle, we can say that the 0, 1 has been seen. Okay. Now, how about higher spins? Have we seen massive particles of higher spin?
1/2 and 1.
Sorry?
1/2 and 1.
1/2?
Electron and weak photons.
Yeah, okay, well, yes, that's right. So protons, but electrons, well, electrons are a different story. You think that they are elementary particles, but really at high energies, they are massless.
Oh, right.
That's the job of the Higgs, right?
I remember that now.
Yeah, but indeed, we have seen many of them, but they are not elementary. Okay, there is a way to produce mass in nature, which is literally a $1 million problem. Okay, so if you're able to solve the problem, the Clay Mathematical Institute will give you $1 million, and the problem is how to show that there are some effects that can produce mass, which account for most of the mass of the proton, most of the mass of the neutron, okay? Because if you just add up the masses of the quarks inside the proton, that doesn't even account for, say, 1% of the mass of the proton. So there is another effect that produces masses, okay? And if you take into account that effect, you can produce particles of very high mass and very high spin, okay? But they are not elementary. We believe they are made of something else, okay? Very good. Now let's go to the massless case. So in this case, we have k squared equal to 0. So what would be a good choice? A good choice would be, say, this one. So what's the little group now? Well, just from looking, we could say, well, something that leaves this invariant would be fine, right? Indeed, that's part of the little group. So rotations on that plane would be fine. So there is a rotation part. But it turns out that the little group is even larger, okay? It also involves 2 more generators, which we're not going to discuss here. So the precise little group is, so this is a subgroup of the little group. It's called ISO2. The I means inhomogeneous. Yes?
So, sorry, I'm probably getting it. In the previous case, we said that. Oh, I see. Sorry.
Okay. So the I means inhomogeneous. And I told you yesterday what inhomogeneous meant, right? When applied to the Lorentz group. When we said the inhomogeneous Lorentz group meant what? Including translations. So here, the I means inhomogeneous too, and it means including translations along the plane, okay? But we're not going to discuss that. In fact, here are some words I don't expect to, I don't expect you to follow everything that I'm going to say right now, which is that we're going to choose representations of this group that represent trivially the translations, meaning our states will not be affected by those translations. That's why I'm not going to derive them, and we're not going to worry about that. But it's important because you could say, well, what if there are particles in nature that transform non-trivially under those translations? Well, the news is that we haven't seen any like that, okay? But it doesn't mean that they are not there, okay? So people worry now and then about that. And in fact, we have 2 faculty members here who recently revisited the case. And, well, if you are interested, you can go and talk to them. One of them is Natalia Toro, and the other one is Philip Schuster. They decided to go back to this basically 100-year-old question and try to understand what these other particles are. But for this course, we're going to stick to the ones that only care about the SO2 part. Okay. For this course.
Question?
So if you want to know more about this, you can ask Toro and Schuster. Yes.
So if there was not trivial representations of these guys, what would that mean? I have some continuous parameter attached to my
Exactly.
particle?
Yes. 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 And we haven't seen any particles like that.
Okay.
So we could have done that with the massive case as well, right?
What do you mean?
Uh,
There is no translations there.
Well, the three-dimensional rotation, but here we are the inhomogeneous part is a translation.
Yes, but it's not obvious. I mean, it's not obvious that it's isomorphic to that, but it's not that that's what we're doing to this, right? It's something that has to do also with the other part. Yes. Yes.
So what exactly are the translations that we're talking about? Translations on the YZ plane, YZ plane?
Once again, I'm not going to discuss it.
Okay.
No, they are not. Yeah, they are not literally those translations. So you have to really work a little bit, maybe for half an hour in a lecture, to get it very cleanly and nicely.
Okay.
Actually, I think I did that 2 years ago.
2 years ago, yeah.
2 years ago, I gave lectures where I did that carefully. Okay, so you might want to watch it. But today, I want to get to something else. So we are not going to do it. In any case, these are the ones that we believe are there. Okay, so this is a rotation, which means that under a Lorentz transformation, okay, so if you have a massless particle, all that can happen is that we get a translation, sorry, a rotation. And nothing else. Okay? So this is for massless particles. So this is what happens under a Lorentz transformation. Now, these are rotations. So we know for sure that if we do a rotation around 2 pi, of angle 2 pi, we should get back the same state. But here, just as in the case of the massive particles with SO3 and SO2, we know that here we could also allow for a minus sign. So we should only require invariance under thetas that are changed by an angle of 4 pi, okay? Not the usual 2 pi. So when we do that, physically, we should get the same state. So what's going to happen? That imposes a condition on sigma. So we should get e to the I 4 pi sigma must be equal to 1. And this is if and only if sigma takes values. Now this is something interesting. Here sigma can take any values that are half integers. Not only positive, but also half integers. In fact, it's not going to fit in here. Right here. Oh, I raised a beautiful picture. I mean, beautiful in the sense that it's the physics of the whole picture is spectacular. Well, that's life. So we are concluding that for massless particles, sigma can take values of this form. Okay. And this number has a name, it's called helicity. Some people like to say that I would like to call this H in this particular case, as in the previous case we call it S. And some people, this is terminology. Some people like to call the absolute value of H the spin. Okay? I don't like it very much. I prefer to say the helicity. Okay? I'll tell you why it's sometimes convenient to say this, but let's just have a look at this list. Now, out of these guys here, which particles have you seen? Do you think we have seen in nature?
Could you elaborate this part about theta plus 4 pi again? So we want to allow for rotations up to that give us a minus sign or a plus sign.
Yeah, the minus sign on the state. Okay.
Minus sign on the state.
The minus sign on the state comes from. Imagine. Let's go back to the case of SU2, right? In the case of SU2, you can pick up a minus sign. There is a transformation that has minus minus in the 2 by 2 matrix, right? That goes as a group element. It goes into the identity of the rotation group, right?
It goes into the identity.
Into the identity of the rotation group. Okay. If you take SO3, SO3 I said is not the same group as SU2, right? SU2 is the covering of SO3, right? So what I'm telling you is that in the Hilbert space, what is actually acting is the SU2. So we should classify objects by the reducible representations of SU2. In the same way, we should also allow not only for rotations around 2 pi, invariance and the rotation on 2 pi, because sorry, I misspoke. It's not that we should only allow for that. We should allow not to be invariant under rotations on just 2 pi. We only have to impose invariance under 4 pi rotations. Okay?
All right. One thing, that
Yes.
expression there, you have U of lambda at P sigma equals E to the I.
Yes.
Sigma comes from where?
Well, it comes from here. We said that under this transformation, all I can get here is this vector with the corresponding little group transformation. And we just said that the little group were rotations.
Okay.
So it has to be a rotation acting on the state. And this is what a rotate. So if you expand this, right, you can think about this as this complex number, right, e to the I theta is the group of all these complex numbers is isomorphic to this group. Do you agree? This is a group of rotations in the plane, right? So these two groups are isomorphic, and this is the way this group acts on a Hilbert space.
Okay.
Yeah, I should have said that, but somehow.
The other thing is why your sigma doesn't change in that expression.
Well, it's quantized. It cannot change continuously. I mean, under a continuous transformation, it cannot change.
We hold sigma fixed for a given case and then go through the theta. Right?
We hold what?
We're holding sigma constant for at a given time and then rotating through the theta.
Isn't that just a particular representation?
Yes.
Yeah, you can think it's a particular. Well, once again, I mean, yeah, maybe it would have been worth going through the whole half an hour of deriving precisely what the little group was, but yeah, no, maybe not.
So how you were saying, right,
Yes.
that just applying an SO2
Yes.
element
To the state.
sigma just rotates your momentum but leaves everything else invariant somehow.
No, it's not. It's not as easy as that. Look at all the work we had to do.
Yeah.
What we're saying is that we can learn how these states transform by learning how the states K transform.
Yeah.
Okay, and how the little group acts on the state K is by doing this transformation. We haven't actually derived that.
Okay.
I was hoping that this would be very well known, and then you would take it as a natural consequence that this was a rotation acting on the Hilbert space. So this is our D. Okay, this is the way the transformation acts on the space. Okay, but once again, this was done in a lecture at some point. Okay. Well, it's important because everything else that we're going to do today and tomorrow is based on that little phase. Okay.
Sorry,
Yes.
to belabor the point.
Yes.
So the top line of the board there has a sum over sigma prime.
Yes.
Whereas, when we are actually applying it to the massless case, that sum has disappeared. And that matrix D is represented by
Yeah, it's just because this is a particular representation. Right. That's right. It's a particular representation. If the little group was, well, let me say, if we go, imagine we were repeating this exercise. After all, we are theorists, so we can repeat this exercise in 6 dimensions, right? 6 space-time dimensions. So what would be the little group? Well, actually, even let's not go to something that we don't know. Say 5 in 5 dimensions. What would be the little group? It would have another 0 here, so it would be SO3, right? So we would actually have J's as classifying the little group of massless particles. So we will have sums over J's here. I mean, sums over the states in the representation J, classifying the way the massless particles in 5 dimensions transform. Okay? It just so happens that in 4 dimensions, the little group is very simple. It's just a rotation, so it's only a phase. Okay? But in higher dimensions, it could be something more complicated, and we will have to actually use the representations will be higher dimensions. In other words, the only irreducible representation of the rotation group in 2 dimensions is 1-dimensional, really. Okay. Very good. So back to the helicities. So we were saying here that these are the possible values of helicities. In fact, particles, this is one particle, this is another one. So this is one particle, this is another particle. They can be treated as different particles. There is no reason why they should be treated as the same. But people sometimes do. And the reason is that there is an invariance in nature, which is called CPT, which means that every time you see one particle of this kind, the theory must also have a particle of this kind. Okay? So that's the reason why people like to talk about the absolute value and put these 2 particles, which in principle are completely distinct, together in a single block and talk about the spin of that particle. So particles with helicity plus minus 2, what do you think they are called? That's right. So we call these ones gravitons. Not that we have seen them, but we believe they exist. How about particles of helicity plus minus 1? So examples are photons, gluons, how about of helicity plus minus 1, plus minus a half? So once again, once we learn more about the standard model, we will discover that at high energies, electrons are actually split into 2, left-handed electrons and right-handed electrons. They are massless, and they have the corresponding helicities. Have we seen anything like this? No. Have we seen anything like this? No. Have we seen anything here? No. Now, the scalar a scalar that is massless and a scalar that is massive are not very distinct. They are not really that different. After all, if you put 0 there, it doesn't transform. It doesn't pick up a phase. And in our massive case, it doesn't transform either. It's a scalar. So the two are more or less the same kind of objects. So it's not shocking we haven't seen it. I mean, we have seen a massive one. So this is borderline. The interesting case is why we haven't seen these ones and these ones. Okay? Hopefully tomorrow we're going to give an argument for why we haven't seen all these guys and all these guys. Okay? So that's the aim of the course. Part of the aim is to show why we haven't seen those particles. But in order to do that, we have to introduce new variables. Yes. Any questions?
Why are gravitons? Why do they have helicity 2, or is it just like something? No.
That's by definition.
By definition.
We call particles of helicity ±2 gravitons. Okay. Well, if you take and why are they called gravitons? Because if you take the Einstein-Lagrangian, right, and you linearize it, and you pretend that this is a theory that should describe particles too, the particles that you will get are particles that have helicity ±2. Yes? Okay. So we're going to end the lecture today with something something I call a clever change of variables. I'm allowed to say clever change of variables here, or clever, because I didn't come up with it. In fact, this was done sometimes in the 80s. Let's see. Here is the idea. Take any massless vector. For no reason whatsoever, I'm going to call it K. Okay? And then construct a 2x2 matrix by summing or contracting with a 4 vector made out of Pauli matrices. Okay? I'm going to denote this 2x2 matrix as K. So this is a 2x2 matrix. So what sigma is was defined in the tutorial. So I'm hoping, or I'm assuming that you all did that exercise. Okay. Now, did you try to compute the determinant of K? Yeah. Yep. And the determinant of K was basically K squared, which is 0 in this case. So that means that whenever we have a massless vector, we have a degenerate matrix, K, degenerate 2x2 matrix. And that tells us that we can introduce new variables. How is that so? Well, because if K is a matrix that has determinant 0, it means that its two rows or its two columns are proportional to each other. So say that the rows are RS. So there is some proportionality constant that relates the two rows. Let me call it M and T. Actually, these S and T have nothing to do with any S and T you have seen before. So it's just that I cannot come up with any other letters. Okay? But, I mean, sorry. It should be the same M. Okay? Now, of course, if I multiply this by M, I could also have multiplied this by something else. I mean, it doesn't matter. So this makes everything more symmetric, so the rows are proportional to each other, and the columns are also proportional to each other. I'm allowing for the most general way of writing such a matrix. Okay? But a matrix like this can be written as the product of two vectors, Tm and Rs. You agree, right? If I just dot these two two-dimensional objects, I get this matrix. Okay. Now I want to call this two-dimensional object lambda of my vector k. And this two-dimensional object, I'm going to call it lambda tilde of my vector k. Okay? So here is a clever change of variables. Instead of using k mu, replace this information by the following information. Okay? That's our change of variables. Now, are these guys uniquely determined once I give you k? What do you think?
No.
No?
No.
They are
I
not.
mean,
No, well, they cannot be anything. Right?
I mean, like, yeah.
Why aren't they uniquely determined?
Because you can have any relative scaling between the two.
Excellent, yes. So if I give you k only, you can come out with this choice, or somebody else can come out with a choice that looks like some rescaling, let's call it rho. And as long as you put the inverse here, you produce the same matrix k, and therefore the same vector k. So there is a redundancy in this description precisely by one complex number. Is that good or bad? Well, let's count how many parameters were there. Okay? Here we had 4 parameters, one constraint. It had to be massless, right? And how many parameters we had here? How many variables? We have 4, right? 2 for this and 2 for this. So it's a good thing that we can mod out by a redundancy. Okay? In other words, we can use this redundancy to fix any of these values to whatever we want, and then be done with it, and be left with only 3 variables. Okay? Very good. Now, everything that I said now, you should be a little bit suspicious. Why? Well, because we know that the entries in this matrix are complex numbers. And this vector was a real vector, right? So when I did this counting of parameters, you should have complained and said, well, but you are comparing 3 apples with 4 oranges mowed out by a pineapple. Okay. So this doesn't make any sense. Well, one way to fix it would be to say, well, let me work with complex vectors in general. Who cares that they are real? Let's make them complex. So my counting will work. Okay? But that's not very physical, you would say. Say, well, I should keep this to be a real vector. Now, if k is real, okay, it's a real vector, what is a property that implies on my matrix k? This implies, or this is if and only if k is Hermitian. Now, for k to be Hermitian, these two guys must be related to each other, right? So for this to be Hermitian, we need, so let's write it here. Now this is a continuation. Now imagine the board is a torus, okay? So we're going here. So this is if and only if this guy, okay, is related to the lambda tilde two-component object by its complex conjugate. Okay? Now the redundancy cannot be any redundancy. The redundancy is only phases. Let me actually call it phi. So if you repeat the counting of parameters, everything should work now. If it doesn't, please don't tell me now. You can tell me after the lecture. No, but it's going to work. Okay. That wasn't. I'm giving you time to check the counting of parameters and see if it works or not. Okay, very good. So what else do we want to do? Right, so we have this change of variables, but you haven't seen why it's clever, right? I mean, it's just a change of variables. So for every particle, now I want to say that for every particle, massless, before we had a state represented by the momentum vector of the particle and the helicity. I'm going to replace this by something that contains a choice of these guys. Okay. So my job now is to show why this is useful. Very good. Before we do that, I'm getting a little tired of saying that these are two component objects. I want to give a name to them before we do anything else. And the way I'm going to do it is to see what happens under Lorentz transformations of our friend here, K. Okay? So in the tutorial, you show that under a Lorentz transformation, our matrix K prime, our matrix K goes into a matrix K prime obtained by applying an SL to C transformation or multiplying by an SL to C matrix on K and M dagger. Okay? You did that in the tutorial, right? Very good. So if we look in terms of what K is with our vectors, with our little two component objects, that's why I want to once and for all figure out who they are. So this one must have, let's actually put it. Let's put a transpose here and then back. Okay? So I would like to say that this is the transformation of our object, lambda, into a new spinor that represents now I'm so eager to change to start calling them what they are. Okay, and this guy goes into this. Now when you have a 2x2 an SL2C matrix acting on a two-dimensional object, this object is conventionally called a spinor. Okay? And when it acts in this form, it's a spinor of positive chirality. And when it acts on this form, it's called a spinor of negative chirality. So lambda tilde is now a spinor of negative chirality. Okay? So from now on, I just did this so that I can call them spinors. Okay? because that's the usual way we call them, and it's very hard to not to say. So from now on, I'm going to call lambdas and lambda tildes the spinors of positive and negative chirality associated with a given vector. Okay? And by that, spinor is the name of a representation. And as we discussed yesterday, whenever I talk about representation, I have to tell you a representation of what? And it's a representation of SL2C. Okay? It's the fundamental representation of SL2C, and we call it a spinor representation. I mean,
Question?
yes.
Should we have a tau, or like a transpose sign on lambda tilde everywhere then, if you're using a transpose sign there?
Yes, here too. That's right. All right, very good. Now we are ready to show why these guys are going to be useful. Let's do it here. Now, given that we have that ambiguity, once again, we're going to use our trick of a fixed vector. That's why I told you that it was no accident I was calling that one K. Once again, we're going to define our P as a Lorentz transformation acting on K and see what that implies on the spinors. Okay? So as 2 by 2 matrices on which SL2C can act, we can define our matrix P associated to this. And this Lorentz transformation would then correspond to some Lorentz transformation acting on our vector K. Okay. Now this guy it's also a little bit annoying to keep track of the transpose all the time. So I'm going to introduce, given that these objects transform differently under SL2C, I'm going to introduce a notation for their indices so that the matrix K has two indices. Of course, it's a 2 by 2 matrix, and their indices are usually denoted as alpha and alpha dot, where alpha takes values from 1 to 2 and alpha dot from 1 to 2. And the dot is meant to represent the fact that on this label, you act with M dagger, and on this label, you act with M. Okay? And therefore, this component, or the 1, 1 component of this matrix, is just the 1, 1 component, or the first component of this spinor, and the alpha dot component of this spinor. Okay? So this is just a notation, and you will see it in many places. The reason I want to do that is that I don't want to put the transpose all the time. I just want to put this here. So we have this acting on K. And this acting on our lambda tilde. Okay? So that means that we're going to define, again, as we did for P, we're going to define a reference. From our reference guy, we're going to define the spinor corresponding to the particle, to the momentum P, as these are. Okay? Just as we did for the representation, when we try to classify the representations. Okay? So here is an exercise. Okay? So So that's why I'm copying it, because I want to get all the factors right, because I want you to have a chance to actually work out through the exercise. So if you apply a Lorentz transformation on P, it's equivalent to this, which is the same as this. Okay. Now we would say that the lambda of the vector lambda p, according to our definition, has to be the 2 by 2 representation of this transformation acting on our lambda of k. Just that's the definition, right? So the exercise is to show that this object precisely becomes this guy, where this theta is the same theta that we had over there, okay, associated to the corresponding Lorentz transformation.
Question?
Yes,
Do you mean mu there? K mu?
yes, thank you. Yeah, you see, even I made a mistake, I was copying it from them. Okay. So after all this suffering I made you to go through, we should see something spectacular happening. Otherwise, you have the right to be upset.
Wait,
Yes.
what is that last lambda with 2 lines?
Oh, so we have a Lorentz transformation lambda acting on P, right? This is a vector, and this is a 4 by 4 matrix acting on the vector.
That's
This is its
exactly-
corresponding 2 by 2 representation. Okay, so when that happens, we have that our lambda for the momentum lambda p is now e to the I half theta lambda p lambda, capital lambda. Now this times lambda k, by our definition, is the original one, lambda p. So we conclude that our spinors transform under a Lorentz transformation as what? Well, you see that if we look at our formula for massless particles, it's as if they transform as something that has helicity a half, as helicity a half massless particles. Let's call them states. Plus an SL to C transformation. Okay. Well, in fact, that's what they were supposed to do anyhow. Okay. Now, the same thing is true for the lambda tildes, except that we pick up a minus phase. Where this action is in the corresponding representation, of course. So this will have to be on the other side. Let's leave it like that. So in this case, we get that this one transforms as a particle of helicity minus a half. Okay? The good thing is that we see that half and minus a half are the basic building blocks of everything that we see over there, right? Because if we have two particles of helicity, two of these objects that transform with helicity half, and we put them together, we seem to get something that transforms as something that has helicity plus 1. So they seem to be building blocks. Now, there will be nice building blocks of what? And that's how we're going to end today. Let's go back to our matrix elements. Of course, here, well, I should have written also the helicity of this particle and the helicity of these particles, okay? Now, if I apply a Lorentz transformation, say, I put here u dagger of lambda, u dagger, I put it here, so this is the identity, and I put here u lambda dagger u lambda, what do I get? I get PA, PB, U dagger, UT, U dagger, U acting on these states. Okay? But this operator acting on this multi-particle state, I'll assume that it acts as something that acts on each one of the states independently. So we know how it acts on these massless particles. So all these ones are now massless, with helicities given by what I told you. So what do I get? I get all these phases. In this case, I get e to the I, sum over, say, m from 1 to n, I, hm, theta, lambda, pm. That I get from these guys, this guy acting on this state. This guy acting on this has the same transformation as the conjugate of this, of u acting on, so this will transform in the same way as u acting on PA, PB, star. Okay? So I'm going to get a minus sign of I, HA, theta, lambda, PA, minus I, HB, theta, lambda, PB, okay, times lambda, PA, lambda, PB. Now the statement that our theory is Lorentz invariant is actually the statement that the T operator is Lorentz invariant. So we get back the same T, and we put the T here, lambda P1, lambda Pn, okay? So this equation tells us that under Lorentz transformations, the scattering matrix of massless particles should pick up phases that are proportional to the corresponding helicities. So this is a very strong constraint. If somebody gives you a proposal for the matrix element of the scattering of massless particles, and they say, well, this is my answer, one of the things that you can check is whether this is true. Okay? So you can check if you perform replace every p by its lambda p, whether what they gave you transforms with these phases. Okay? So this is the aim. We should construct things that transform in this way. Now, going back to our spinors, we see that our spinors could be building blocks of things like this because they transform with the smallest possible value of helicity. So if we do sorry, I want to put, well, I'll do it manually. Okay, so that's the aim. We want objects that transform in this form.
Right.
Yes.
Can you repeat one more time why the T matrix was invariant?
That's a statement that our theory is Lorentz invariant. Okay, remember that that's the way an operator transforms under a transformation, right? So we are going to assume that our theory is Lorentz invariant. Do you agree that that's the way an operator transforms? I mean, the
But
T.
Isn't that saying that it transforms the scalar? But,
Well, it's an invariant.
oh,
So the T,
so you want
the operator T. I mean, this is the definition of T prime, the
Right.
transformation. But the statement that the theory is Lorentz invariant means that T is invariant under that transformation. It doesn't mean that the matrix elements are invariant. In fact, they are not invariant. You see, they pick all these factors, right? Of course, the mod square of these things is invariant, which is a statement we made at the beginning of the first lecture. Okay. Now, let's finish this lecture by realizing something interesting. If we want to build something that transforms correctly under the Lorentz group, we can perhaps, instead of using momentum, we can use these guys as variables to determine these matrix elements. There is a problem, though, which is that we only want something that transforms with these phases after we replace the lambdas, after we replace the momenta by the p's. And here I'm thinking about moving these phases to the other side. After we replace the lambdas by after we replace the p's by lambda p's, we should get something that picks up the phases. Okay? In other words, let me write it here. We need a function such that when we replace the p's by lambda p's, we get phases proportional to the corresponding helicities. So whatever the function is, it must be a function that when we make this replacement, we get this factor in front, okay? And nothing else. So we have to find ways of producing these factors without producing these lambdas. These lambdas are annoying. So we have to get rid of those lambdas. So in the tutorial, you will show that if you have two vectors, say PA and PB, actually, let's just call them P and Q, because they can be any two. They don't have to be these two. They could be any two. And their corresponding spinors okay? The magic objects will be the following. Will be the determinants of, you put this, the first component of this spinor here, the second component of the same spinor here, the first component of this spinor, and the second component of the spinor Q. This determinant, which people like to call PQ, so this is a definition of what this determinant is, transforms as follows. Under a Lorentz transformation, using our definition there, goes into e to the I half theta lambda p plus lambda q pq, and nothing else. So this determinant transforms as if we had a little matrix element of particles with helicity plus half. Okay? Now the same can be done for the tildes. So I can put tildes everywhere. And people denote this by this kind of bracket. Okay? So the conclusion of the lecture today is the following. These guys are SL to C invariant. Oh, that's what you're going to show in the tutorial, that these objects are SL to C invariant, meaning that these will drop out when we perform this transformation. The only thing you will pick up will be the faces, okay, under the replacement of P, lambda P by lambda of capital lambda P, okay? So we're going to have this. And the conclusion of the lecture is that any object, any S matrix element here is a conclusion. Any PA, HA, PB, HB, in fact, I wrote it like that, but I should have written lambda of PA or lambda A for each one of them, okay? Because remember, now the data is given in terms of lambdas and lambda tildes for each particle. This, whatever it is, in order to have the correct transformations under the Lorentz group, it must be a function remembering our rational function approximation is a rational function of all these brackets, such that when we perform a Lorentz transformation, we pick up the correct helicities. Okay? So this is it's actually amusing. Now we can simply choose helicities for particles and start to classify all possible rational functions that we can make out of these products so that they transform correctly with the corresponding phases dictated by the helicity. Yes?
So there, it was, those invariants were constructed from pairwise, association of momenta. So what if you have odd number of particles in this transformation?
Oh, these are all possible ones, right? Say you have two particles here and you have three particles here. In fact, in the tutorial, you will have the case when you have two particles here and only one particle here, right? So in the case, well, that's pretty good. Imagine you have particles 1, 2, and 3. Okay? Now I'm changing labels. They are not A, B, and 1, 2, 3. Let's just say 1, 2, and 3. So this will have to be a function of the brackets 1, 2. What else? 1, 3, 2, 3, 1, 2, 2, 3, 1, 3. Okay? So you can start playing with these things. You can start multiplying them, produce rational functions, things in the numerator and in the denominator, in such a way that under a Lorentz transformation, when you apply this, you see this guy will pick up every time the label P appears in a lambda in the numerator, it will produce a power of a half of the phase you need. So if you have a particle of helicity 1000, how many times you need the label of that particle to appear? You would say that, well, you would need it 2000 times. Right? You agree? You don't look very convinced. Let me give you an example. If you have particles of helicity, say particle 1, in this whole problem, or particle A has helicity 3, maybe 3 is too much, say helicity 2, okay? Well, there is a catch here because these guys are on the left. So according to our transformation, they should then pick up a phase of the form e to the minus. Under a Lorentz transformation, they should pick up a phase of the form e to the minus 2 times I theta. Okay? So this particle has helicity 2. It should pick up this phase. Well, if I claim that this function has a with something, a times something, how many times do I have to put it in the numerator in order to get this phase? Well, actually, I'll be in trouble because there is no way I can get this phase if these guys are in the numerator. So where should they be?
Denominator.
They should be in the denominator. How many times they have to appear? They have to appear 4 times, right? Because each one of them will pick up a phase of I half, a phase of a half, and then we need a minus 2, okay? Now you would say, well, but you could also have put these guys, and then if you use them, you will produce positive guys even if they are in the numerator. So there will be many possibilities that you can choose to construct these objects, but it's just a game of homogeneities, right? So we are declaring that we're looking for rational functions of these objects that transform correctly under